So today we will switch to Chapter 8, Analysis of Oriented Patterns. In the course I give in Calgary, usually I don't come this far, but we have been going a little fast and skipping some details. As I said, if you want to discuss any of those, we can do that separately, or you could read the notes. I put more detail here than needed for a lecture. We have done quite a bit of work on analysis of oriented patterns in our own research work, and for that we went back and read the literature in this area and did some analysis and developed some of our own methods more for analysis of oriented patterns. As we worked on several types of biomedical images, we found that there are such patterns in several images where we could use directional analysis or analysis of oriented patterns or oriented texture. So some of this material is based on our work. Most of the illustrations are from our own work. My own students have done quite a lot of work in this area. So the main point here is many images are composed of piecewise linear objects or curvilinear objects, curvilinear features. They are linear for some distance and then they curve and then the curvature changes, but then there could be another linear portion. So a curved pattern could be made up of a number of linear segments. So it is piecewise linear. And linear or oriented objects possess directional coherence or correlation. They are coherent in some sense of some property, or the values are correlated in that direction, not in all directions. And that can be quantified and examined to study the underlying pattern or texture. Sometimes we may not want to call it texture. Texture has some very specific connotation. So here, when you have these ligament patterns or fibroglandular tissue, is that texture like what we would mean in terms of something printed like that shirt or some of your dresses? That is a different kind of texture. This is not so clearly texture, so that's why Rao in his book has called this weakly oriented structures or weakly structured texture. So in texture segmentation, which is a fairly large topic in the literature, a common approach that's been used to identify differing regions is to find the dominant orientation of the texture elements. And directional analysis is useful in not only the identification of oriented patterns, but also image segmentation and characterization of oriented or weakly ordered texture. So let's look at some oriented patterns in images. In many cases of natural materials and also artificial man-made materials like clothing or ropes and threads and so on, strength is derived from highly coherent or organized or oriented fibers. When you take a rope, there is an ordered pattern of the fibers in the rope. If you take a small section, you have parallel lines, but then overall there is some braiding. A normal healthy ligament is composed of bundles of collagen fibers. I showed some pictures earlier and you will see more of them, that are coherently oriented along the long axis of the ligament. The ligament is only this long, but we are talking about fibers that are a few tens of nanometers in diameter. An injured or healing ligament, on the other hand, contains scabs of scar material that are not aligned. They are collagen fibers, all right, they are deposited in the healing process, but they don't have that orientation, and the preferred orientation develops slowly over time. I'll show that. So the determination of the relative disorder or order, is there order present or is it disorder? And you need to characterize that. Of collagen fibrils or fibers could provide an indicator of the health, strength, and what is called functional integrity. Can this function and bear the load of normal activity or sport activity if one is engaged in football or soccer or hockey and so on? So a few examples: fibers in muscles and ligaments. Fibroglandular tissues, ligaments, vessels, and ducts in the breast, and vascular networks in ligaments, lungs, and the heart, and bronchial trees in the lungs. There are a number of figures in the notes that you can refer to later on, and we have gone through some of them. So in man-made materials such as paper and textiles, again, strength or just the object like paper. In paper, you're not looking for strength. You don't want it to rip easily, but still, it's not strength, but the very existence of that sheet of paper depends upon individual fibers that are somehow put together in some order. The strength of the material is related to the organization, not necessarily always parallel, but there is some organization, and that constitutes that material. So information related to orientation has been used in remote sensing to analyze satellite maps or aerial photogrammetry for the detection of anomalies or even structures, man-made patterns and natural patterns like rivers, buildings, and farm land, and so on. So because man-made structures tend to have strong linear segments, then directional features can help in the identification of these structures. So how do you measure this? How do you characterize directional distribution? We know that when you measure a gradient, like using the Sobel operator, if you just take one of them, you get the x derivative, the other gives the y derivative, put them together as the derivative of x plus j times derivative of y. You get a complex quantity. Magnitude gives just the magnitude, but the angle gives you the arctan of the ratio of the imaginary part to the real part, gives you the orientation or direction of the gradient. So how do you characterize a distribution of that? Typically against angle, magnitude is separate. Statistical measures used in the rectangular coordinate system may not be suitable. So we need to switch to polar coordinates or some angle-based coordinate system. And another question arises, do you want to go 0 to 360 or 0 to 180? In most cases, 0 to 180 will be suitable because a line going like that could be oriented that way or this way, it doesn't matter. So we could limit our analysis to half the circle, 0 to 180, or if you prefer, plus minus 90 degrees above the horizontal, depending on the application. The Rose diagram is a graphical representation of angular distribution of something, of directional data. So corresponding to each angular interval or bin, there is a sector or a petal of the rose. It's not a rose, but it's called a rose diagram, and it is plotted with that either the length of that petal or the area of the petal being proportional to the data in that angular band. So the radius could be made proportional to the area of the image components, or the area of each sector could be made proportional to the square of the directional data, depending on what you want to represent and how you want the plot, the Rose diagram, to look like. You could also compute what is known as the principal axis. So I have this object, and if it is vertical, then there is a principal axis like that. Or if it is like this, the principal axis is that way. So the orientation could be orientation of an irregular object, could be formulated or identified by taking moments and finding the principal axis. So the moment of inertia, or the moment as we saw earlier, of fxy, but now with respect to an angle, theta. So m theta, integral over all space, x minus x bar, the centroid, sine theta, y minus y bar, cos theta square, fxy dx. So this is moment of inertia about that line, which is passing through the centroid and at that angle theta. And if the object has preferred orientation, then there will be a large moment at that angle. If it is a perfectly circular or spherical object, there is no preferred orientation. A ball has no preferred orientation, whereas an ellipse has, this thing has a preferred orientation. There is an axis. Of course, you can say there is a long axis and a short axis. and you will take the long axis as the orientation. So to make m theta independent of the choice of coordinates, then you could let x bar, y bar be 0, and then you get this equation, and go through that, expand the square, and you get the second moment is 2, 0, 1, 1, and 0, 2. And MPQ is the pqth order of the moment, as we have seen before. So you go ahead and solve that, you get tan 2 theta is 2m11 over m20 minus m02. So by computing these moments and solving for this equation, we can find the slope or direction of the principal axis of this object, which is, the principal axis would be like that. Now, an image might not have simply one object with one orientation. There could be multiple objects. Then what you do? Then you get some average measure. If there are many of these objects present in the image at multiple angles, then it is hard to say what is the orientation of the image. Then you may want to detect each one of these and get the orientation distribution of all of these objects in the image. To do one such axis for the entire image may not be meaningful. So the previous discussion assumed there is one object in the image. But if you have 50 of them, then if they're all aligned in the same direction, fine. But if they have different orientations, then you get some average value. So if there are a number of directional components at different angles, then theta will represent their weighted average direction. It cannot detect the existence of components in various angle bands, so this is not very useful in practice. You could take angular moments of an angular distribution. You can get angular distributions of some representation of the image. For example, the Fourier transform. We saw the Fourier transform for a rectangle has its, or a line has its components concentrated along a line that is perpendicular to the orientation of the line in the image domain. So if you convert the Fourier transform into the polar coordinate system and get a function of r theta, at some angle there will be a large concentration of energy. So you can plot the concentration of energy, or just the energy of the power spectral energy or power of the image. In signal processing, power and energy are related by the time. Power is energy divided by time. In images, there is no time. So do you want to call it power spectral density or energy spectral density? That distinction is not made. So sometimes I may mix energy and power. Here, they are the same. One could be normalized if you wish, but that doesn't matter. We are only looking at the distribution. So suppose somehow you got this distribution, Pn. Pn is the normalized weight or probability for the nth angular band. 0 to 180 degrees, you may break into 10 bands of 18 degrees each, or 18 bands of 10 degrees each, how many ever bands you want. And theta n is the center of the nth angle band in degrees or radians, as you wish, and take the moment. N is the number of angle bands. That is a moment of the angular PDF, angular probability density function, or distribution function of some kind. You will see examples of this as we go through this chapter. And then, in most cases, you would want the principal axis, so take the average. That will give you the main axis of concentration of energy in that probability density function if it has been normalized. You are also interested in the dispersion. Is it concentrated only in one angle, or is there some spread around that angle, or is it spread all over? For that, you take a variance in angle, theta n minus theta bar square times Pn. These are all the same as the probability density function moments that we saw earlier. But now the interpretation is slightly different in that this is an angle and this is the probability or proportion of some measure occurring in that angle band. Okay? Now when you have two distributions, P1 containing P11, P12, P1n, then you can see this as a vector also. It's in the discrete representation, it is simply a series of values. So it's a vector. You can compare one vector with another using distance measures, Euclidean distance or any other distance you like. So you may treat the Rose diagram or the angular distribution of whatever it is you're measuring, get the moments, treating it as a PDF, but you can also treat it simply as a vector. I computed 18 values with angle band of 10 degrees, 0 to 180. I computed the energy or something. So I have a vector with that dimension for this image and that image and so on. I won't compare the images. You compare these vectors and take some distance between them. So you can take the distance P1 with reference to P0 as this Euclidean distance. Or the Manhattan distance is just taking the absolute value of the difference instead of squaring. So you're comparing vectors derived from the images now. But the vectors are made up of the angular distribution. Okay? Now this could be some standard reference, or it could be P1 minus P2, one image comparing with another image. You can take entropy, like we have seen before, Pn log Pn. If it is uniformly distributed, it has no preferred orientation, it is isotropic. Then the entropy is maximal. If energy is concentrated in only one angle band, there is preferred orientation, then entropy is small or minimum, if it is only exactly one band. So the entropy is not giving the angle band of primary orientation or the principal axis, but it gives you the spread, similar to variance that we saw. Variance is also a spread. Entropy is also a measure of spread of the distribution. All right? Any questions about this? Okay, so how do you get directional components out from a given image? We have seen the Fourier transform of an oriented linear segment is a sinc function. If it is a straight line, it's a sinc function only at that orientation, at the corresponding orientation in the frequency domain or along the corresponding axis. But if it has a certain thickness, then there is another sinc function in the orthogonal direction. Two sinc functions multiplied. So based upon this property, we can say we can select components at a certain angle. Now displacement, if there are several lines at multiple displacements for the same angle, they will all add up and the Fourier transform will have energy in the same angle band, all of them combined in the same angle band. If you take the magnitude spectrum, phase is different. So the magnitude spectrum will remove the effect of displacement, and all straight lines of the same orientation will have energy in the same angle band. If the angle changes, the orientation in the frequency domain changes. So we can select linear component specific angles by putting a filter extracting Fourier domain components at in a particular angle band. If you put an ideal filter, we get ringing artifacts. We saw that. So the filter has to be shaped appropriately to have smooth transition from the pass band to the stop band. So here are two line segments. This is on a discrete grid, a digital image, and it's been cut. So when you cut an image like that, it's like putting a window. And putting a window means multiplying this line, which perhaps is going plus minus infinity, but we put a window, so that means multiplying that line with a rectangle function or a square function. So the Fourier transforms of the two will be convolved. The Fourier transform of the line is a sinc function, all right, but it is convolved, Fourier transform of that line will be a 1D sync function in that orientation, but the Fourier transform of the square window or rectangular window you put is a 2D sync function. The two are convolved and there is spread in the other direction. Or if the line has thickness, the same thing happens. So the Fourier transform of a line that is in a finite space digital image or discretized image will have some other artifacts. But still, you can see that most of the energy is here, and if you take only that part, it represents this line. If you rotate it, then there is a corresponding rotation. Note that the energy in the frequency domain, this axis is perpendicular to the orientation of the line in the image domain. There are some studies on the human visual system that have shown that we have orientation selective structures. Whether they are Gabor filter-like filters, bandpass filters, it's not clear. Some have suggested that. So Marr showed that the orientation of linear segments, primarily edges, is important in forming a primal sketch. So when you see something with high contrast, black pattern on white, and then you close your eyes, you will have a pattern of the edges only. And sometimes you may be able to see multi-scale versions of that. So stare at something like that black frame for a number of seconds, and then close your eyes, you will see the inverse of that, because we are doing some edge detection. And there are some other artifacts also. Color, there could be some reversal of colors. If you refer to my color image processing book, and if there is time, I'll include a seminar on color image processing at the end. So Marr called it the primal sketch. All of that information is sent. So it is not just the picture, the intensity information that is sent from the retina to the visual cortex in our brain, but some other processed versions in between. There are some filters, and there is some neural encoding and data compression, and that information goes to the visual cortex. That's been suggested by a number of researchers. So other researchers have used oriented bandpass filters to simulate the human visual system. What are oriented bandpass filters? Gabor filters, which we will see in detail later on. Subhashish Chowdhury, who did his MSc with me, and later on he came back and he was the director of IIT Mumbai, he used a set of bandpass filters to obtain directional components in electron microscopy images of ligaments. I'll show you that. And one of my colleagues, Dr. Bruton, designed high-quality fan filters. Fan meaning an angle-specific, a filter with a passband that is a sector in the Fourier domain. I'll show you that. So let's look at sector filtering in the Fourier domain. So let's look at a line segment of some orientation A and y-axis intercept B in the xy plane with some limits plus minus x plus minus y. The equation is y equal to ax plus b, and let x be equal to y, so it's a square image. This is just the formulation of the image like what I showed you. So fxy is equal to 1 along the the line, y equal to x plus b. So let x be y minus b over a, then the Fourier transform comes out in this manner with a sinc function. The exponential factor depends upon the placement of the line. There is a phase shift depending on your origin. So this is just a phase factor. This is some scale factor depending upon these parameters of the line. But we are more interested in this sinc function, u over a plus v. So there is a relative scale factor of a between the two frequency axes. That shows the preferred orientation. So the Fourier transform of the line is a sinc function with an argument that is a linear combination of the two frequency variables with a slope that is the negative reciprocal of the slope of the original line, which is this 1 over a. So it is not symmetric anymore because a line is oblong, not a square. It's a very thin rectangle. The intercept is translated to a phase shift B over A in the U variable. The sinc function is oriented at 90 degrees to the original line, centered about the origin, regardless of the intercept of the original line. Like this. Doesn't matter where the line is placed. If I push this there, you get the same thing. If I displace the line, you get the same thing in magnitude. The phase factor is not displayed. If I rotate the line, this also rotates. So this allows us to form filters and say, I want only components in this angle band. Of course, you must have conjugate symmetry. You have to pass the negative frequencies also. So spatial components in a certain angle band may be obtained by applying a bandpass filter in an angle band perpendicular to the band of interest and then applying the inverse transform. What should be the shape of that filter? We will see later. A spatial offset of the lines would only result in a phase shift. The magnitude remains the same, and filtering typically is done in magnitude only. You let the phase be the same as in the original image. So this is a fan filter in the frequency domain. This is the horizontal U axis. This is the vertical V axis. DC is here. This is called a fan, like the blades of a fan when it's not running. So there is symmetry. Positive U, a positive V frequency, negative V frequency, positive U frequency, negative U frequency. Okay? Symmetry in both U and V. Not isotropy. I'll skip some of this review. The problem with the Fourier domain technique is filters don't behave well with occluded components. If there are two lines like this, what is the orientation at the intersection? There is no orientation there. You need a certain length in order to define orientation. And if there are multiple occlusions, one line superimposed on others, then there is a bit of a confusion in filtering and you may not get good results. Again, it depends on the filters you use. Smearing of line segments occurs, and that leads to inaccurate results when inverse transformed, and typically you would apply a threshold later to detect only the lines. And we have such problems. There is truncation artifacts and spectral leakage because the bandpass filter will be removing a number of components and there is some transition. It cannot go like that forever. Gabor filters do, but at some point you have to cut it off, and when you cut the filter, there will be ringing in the inverse transformed image. There will be truncation artifacts and spectral leakage when the linear segments are truncated in the image domain. The spectral components are smeared. When an image is truncated with a window, the Fourier transform of that object, which we assume is much bigger than that window, will be multiplied by the Fourier transform of that window, which typically is a square or a rectangle, which has a 2D sinc function as the spectrum. So the spectrum of the original line or pattern is convolved with the spectrum of the window, which is a sinc function, and that sinc function will just mess up the spectrum through convolution. The same thing happens in 1D. When you truncate a signal, the spectrum is not the real spectrum anymore. And truncation may not be by applying a window, it is just that we start observing here and stop observing there. Signal has been going on. So just that is a window, an implicit window. So there are these artifacts. So Chowdhury designed a filter to minimize such artifacts. We broke the spectral domain into 12 bands of 15 degrees each, and we made a combination of the fan filter, like you saw before, but the fan filter is ideal. You want to make that transition smooth. So we put a cosine function in the angle. But the cosine function also ends there. There is a certain bandwidth given to it. Theta minus theta naught is the center of the band, and it is smooth up to a certain distance or certain angular separation. And then this is a Butterworth bandpass filter. There is a low frequency cutoff and there is a high frequency cutoff. We saw the Butterworth filter earlier. Here we're using just the frequency f. We're taking a ratio, so it doesn't matter whether it is omega or f, but in image processing, the 2 pi factor will be cancelled out anyway. So there is a low pass filter and a high pass filter, and that combined will give you a band pass filter. And then there is a ramp here. It's a ramp with 1 minus beta FR. FR is the radial frequency. So it reduces. So it's suppressing some high frequency components. We have a low pass filter, but still we are putting another filter on top of that. So it's a combination of an ideal fan filter, which is defined in angle there, but with a raised cosine window weighting. It's a Butterworth bandpass filter with a low pass and a high pass component, and a ramp shaped low pass filter, which is this. So there are all these parameters that we had to specify in order to get this filter. You don't need to worry about all these specifications. For a certain application, these are the parameters we used, and the filter looks like this. So this is the bandwidth of the fan filter. The gain reduces as we go to higher frequencies. The gain reduces as you go away in angle from the center of this angle band, and the gain also reduces as you come towards DC. There is a high pass filter. There are 2 low pass filters, the ramp and the Butterworth, and the cosine weighting makes it smooth. Now, oddly enough, at that time when we designed this in 1985 or 86, we were not aware of Gabor filters. Gabor filters in 1D had been published in 1940s, but in 2D, the important papers in Gabor filters came a little later or around the same time, and we had missed that. I need to check whether it came later or at the same time. So we designed our own combination to make this filter as smooth as possible. Later on, we switched to Gabor filters. If we had known Gabor filters at that time, we would have used them. So this gives you 12 angular component images. One forward Fourier transform of the given image, 12 filters are applied, and 12 inverse Fourier transforms have to be computed. At that time, that was a lot of work for the wax computer we had. And the university was getting supercomputers, first array processors, and then parallel processors. So Subhash has spent a lot of time learning. I also went and took those classes to write programs for array processors in supercomputing. And then later on, we parallelized some of the algorithms when the supercomputer switched to parallel machines. Now, it doesn't matter. Speed of these things doesn't matter. Ordinary computers can handle this fairly easily. And the pictures were not that big. They were 400 or 500 pixels on each side. So each component contains the linear components of the original image in the corresponding angle band, corresponding meaning perpendicular. There will be some artifacts, so you need to threshold, and Otsu's thresholding method, which is very popular. I mentioned Otsu's paper has a high number of citations, although it is a short communication article in one of the IEEE transactions. Do you want me to go through Otsu's method? No. Otsu's method is a thresholding method, and the details are here. I'll skip that. It gives you an optimal threshold based on some measures of variance and mean of the distributions, mostly variance. The mean also comes in, and some prior probabilities. So I'll skip all of that. So here we have a test pattern we made up. In all of our works, we have used test patterns that we make up so we understand what is happening. What will happen with some image where we know we have multiple directional components of different thickness, thick and thin, and different orientations and substantial masking or overlapping. These lines at 135 degrees are overlapped by all of these. So detection of those is difficult. So this is the Fourier transform. The vertical lines are here. There are thick vertical lines, so there is a spread. The horizontal lines will be there. The 45-degree lines will be here, and the 135-degree lines will be there. All of them, regardless of position. So if you extract the 135-degree components in the frequency domain, this is what we get, the 45-degree components. Now there is overlap. Note that there is substantial overlap for these. But still we are getting this. The overlap is more here, so there is a bit of a confusion there. You apply a threshold, we get fairly good results. Not perfect. We computed the error between this and the design straight lines, and we computed some error measures. In my lectures and seminars, I don't go through all of those error measures. They are for the sake of publication. You give that, they're on the book in the notes, but I don't read all of that. Not necessary, but you need to quantify what is the error, measure it and show, analyze. So the vertical band, we get this. For the 135 degree, we lost some. There is substantial overlap. You can't even see there. The contrast of these lines is poor. So that happens. So the error is high for this band. For the others, the error is not so bad. Dr. Bruton and his colleague, they designed fan filters as digital filters. I won't go through all of the details here, but the transfer function in the S domain, Laplace variable, is defined as a ratio of two polynomials where PQ are the coefficients and S1, S2 are the Laplace domain variables in the two directions, horizontal and vertical. And there are some conditions. They have to be rational, they have to be continuous functions. But these functions, these filters, let's go back to the original. They're not continuous. They cannot be continuous in the sense and differentiable because you want zero gain there. So if you go in this way, you want zero. If you want in that way, there has to be continuity, and there is no continuity because DC is set to zero. And if you take here, there is a discontinuity. But within the passband, you want continuity. So there are some contradictory or conflicting requirements in filter design. Computationally, you just go ahead and do it and you will get some artifacts. Deal with the artifacts, thresholding. But if you want to design a stable filter in the digital filter paradigm, then there are these other considerations that come in. So I will just leave it at that. It is transformed to the Z domain through a bilinear transformation that you would have seen in 1D digital filters for each of the directions, horizontal, vertical. So you get some coefficients BM and AM, and Z is the Z domain variable, Z1, Z2 for the two directions. Bruton and Bartley came up with a design, and I won't go through that, and they gave these numbers in their publications. And we implemented them and used them, but then we found that some recursion may help. If you just do it once, you may not get the best image, but if you were to apply it again, you may get a better image. So William Ralston, who did his MSc with me, came up with a transformation to apply to change the direction. You need to take that as a basic filter and rotate it to angle theta. So he used this transformation to rotate the filter. I'll skip some of these details. Some of these conditions put in the angle band, pass band are shown there. But this is a fan filter. So with this, with the same test image, if you apply one pass, you get this with the vertical direction filter. If you apply 9 passes, you get this. So as you iterate the filter, these other bands, out of band details are suppressed, and you get a stronger response in the pass band of interest. So that was the advantage of this method. Whereas if you take the Fourier transform, apply a filter, that is one shot. You can't do anything more. Whereas with these recursive filters, you can apply again and again. Repeated passage will suppress the unwanted components and boost the desired components. Or, I think I should just say suppress the undesired components. The gain will be multiplied over and over again. So the unwanted components are suppressed. There are still some artifacts you can see. But that's after 9 passes of the image through the filter. Now, Gabor suggested filtering in 1D signals. It was in 1941 or 42. His first papers were published. He suggested that the use of time-limited functions as the kernels of a transform instead of the unlimited sine and cosine. Time-limited in the sense they are still modulated with the sinusoid, but they decay. Whereas the sine and cosine functions in the Fourier transform, they don't decay, they go forever. So the sinusoids are weighted with a Gaussian function. Now the Gaussian function is also of infinite spatial extent, it goes on, but the exponential weighting factor makes them very small after some displacement, depending on the sigma value. So yes, they are unlimited theoretically, but in practice those values are so small after some displacement, you may stop at some time. Whereas the sinusoids in the Fourier transform, you cannot stop, they go forever. So there is, Gabor showed that complex sinusoidally modulated Gaussian basis function. Or you can turn around and say, is the Gaussian modulated by a sinusoid, or is it the sinusoid that is weighted by a Gaussian? You can see both ways. They satisfy this time bandwidth limit, delta t, delta f greater than or equal to 1 over 4 pi. This is known as the uncertainty principle, and in 2D you get this product of 4 delta functions in x and y and u and v greater than or equal to 1 over 16 pi square. So these are measures, some measures of spatial resolution and frequency resolution. In essence, what it means is, if you have a time-limited function, its frequency response or Fourier transform will not be band-limited. A time-limited function is a rectangle function. Its Fourier transform is a sinc function going forever. Not DFT, but continuous domain. If you have a time unlimited function like a sinusoid going forever, its frequency can be band limited. It will be just 2 impulses. The Fourier transform for sinusoid is sinusoid has positive frequency, positive, and negative frequency, negative value. Cosine, both will be positive. But they are band limited strictly, just in fact absolutely band limited because they are delta functions. An infinitely long time domain function is a constant, DC. Its response is just an impulse at DC. It's completely, totally band limited. And completely time limited function is an impulse, and its Fourier transform is a constant forever. So there is this duality, and the product of those will be greater than or equal to 1 over 16 pi square, which says you cannot have a time limited function whose frequency response is also band limited. That is not possible. You will make some sacrifices by cutting one of them. Gabor functions provide optimal joint resolution in the time and frequency domain, or space and frequency, depending on your formulation, and can form a complete basis set through phase shift and scaling and or dilation of the original basis function, or now called wavelet. But Gabor is not, we are not using Gabor as a transform. We're not getting all coefficients with all possible functions like we do with the Fourier transform. We don't need that. We can select certain Gabor functions of certain orientation and certain scale factor and use only those. It's not a complete representation. Reversal is not required in image analysis. Reconstruction of the original signal from these coefficients, if you want to call them, the filtered images are actually images. They're not individual coefficients. But we don't need an infinite collection of them, and we don't need to go back to the image domain from these components. So we can select a subset. That's what is done in wavelet analysis. You take a finite set of wavelets, and from experience or experimentation, you know these wavelets of such and such scale factor and bandwidth or frequency will be enough for this application. And you use only those. You cannot go back to the original signal from those limited components. So the set of function forms a multi-resolution basis that is referred to as a wavelet basis. That came up much later. Gabor wrote his paper in 1940s. And Dogman extended Gabor functions to 2D sinusoidal plane waves of some frequency and orientation in a 2D Gaussian envelope. And they have been found to provide good models for the receptive fields of simple cells in the striate cortex. So there is some relationship between these functions and what happens in our visual system. So let us look at a few formulations. We saw one formulation earlier. For the detection of the pectoral muscle, I showed Gabor filters as wavelets. That is one formulation, and we will see another formulation later when we talk about architectural distortion later in this chapter. Depends on how you want to implement and how you want to interpret the results. So we can say HXY, the impulse response is GX prime Y prime, the Gaussian, with an exponential function, like in the Fourier transform, but this is simply a complex sinusoid. It's not the Fourier transform. It is one frequency U, one frequency Y, and this is cos and sine as before. X prime Y prime with reference to X and Y is a rotated coordinate system with angle phi. X cos theta, X cos phi plus Y sin phi minus X sin phi plus Y cos phi. That is just rotation of XY to X prime Y prime by angle phi. The Gaussian is this. But now, the Gaussian doesn't have to be isotropic. The Gaussian is a bell-shaped function in 1D. In 2D, it has another factor on the other side, but if you want preferred orientation, you want to detect things along a certain angle, then you don't make this Gaussian isotropic. We say we will have a bell-shaped function of this size here, but in the other side we'll make it narrow. Then that bell is squished, and it'll have some preferred orientation. So this Gaussian now is not x squared plus y squared, but x over lambda squared plus y squared. Lambda is that aspect ratio. You can multiply with lambda, it doesn't matter. You just define it as the inverse of this value. Multiply, divide, it doesn't matter. It's a scale factor between x and y. So the aspect ratio lambda. U and V are the center frequencies in the frequency domain as modulated by this exponential function. It is modulation in the sense that introduces a phase shift, like in amplitude modulation. Do you still study AM radio in communication theory? Yeah? Yeah, so you multiply the given signal to be transmitted with the carrier frequency, and it is shifted to the carrier frequency so the signal can be transmitted. So these are the frequency values of the modulating function. So you can say, yes, this is a Gaussian modulated using a complex exponential. If you don't want complex, you just use sine or cosine. That's fine too. So you're shifting the frequency. Gabor functions act as bandpass filters, I already showed that, with directional selectivity because of that factor lambda and theta. There is the preferred orientation implied by the fact that it is not isotropic. And the frequency is shifted by the modulating function. The frequency domain is usually divided into a symmetric set of slightly overlapping regions at octave intervals or however you want. I showed those ellipses in the frequency domain. You want to span the full frequency domain and you want to allow overlap between the adjacent Gabor filters so that you don't miss components in between. I'll skip some of these other details. So this is what the function looks like in as a mesh plot. So it is a Gaussian envelope modulated with the sinusoid and in the other direction too, but they are not the same in the two directions. So you can imagine, depending on the rotation, this is broader than the other side, which is implied by this scaling. In the frequency domain, this is the kernel function, the same as an image now, bright in the middle and dark on the side, negative side lobes, bright again. So it is like a sync function, it goes up and down, but the weighting is not sync but Gaussian. So there are these, but you cannot see them. You can see them here. Positive, negative is going down, you can't see positive, and unless you rotate it, you won't see the negative part. But it has negative values. In the frequency domain, we get these ellipses that are sort of sections of the Gaussian located at those center frequencies, displaced by the UV of the modulating function. And the scale factor determines the size of these. So from low frequency, you go to medium to high, and you can put them at various angles. Okay. Is it a square? Or has it been stretched with? Well, is that a circle? It is? Okay. That's okay. Now we're not doing shape analysis, so it's okay. So multi-resolution signal decomposition becomes possible because there is a factor of this resolution in the scale factor. So you start with a wavelet, and then fine temporal or spatial analysis is performed with contracted versions. Make the wavelet smaller and smaller and smaller. Fine frequency analysis is performed with dilated versions. You want to reduce the bandwidth, then you make the wavelet bigger or slower. Then the bandwidth is reduced, and so the filter becomes narrower, and you need more of them. So you get better or finer frequency resolution. The definition of a wavelet is flexible. So in the literature, you have seen many types of wavelets. There are some requirements. The function must have a bandpass transform. There are a few other admissibility criteria. I think I've stated some of them earlier. It depends upon which of those are relevant in your application. Some may not be relevant in filtering without the need to reconstruct. So a wavelet at a particular resolution acts as a bandpass filter, including Gabor. The bandpass filters must have constant relative bandwidth or constant quality factor. This is important in auditory and visual systems. In the case of non-stationary signals, you need to compromise between how well transitions or discontinuities can be located and how finely long-term behavior can be identified. In the case of speech signals, I mentioned there are plosives that are transients. So if you use a big window, the transient will be lost in that big window. So you want a small window. But if you use a very small window, you'll be looking at maybe one of the wavelets of the repetitive function in the case of voice speech. You're not looking at the entire voiced signal. So there are these conflicting or contradictory requirements, and that is related to the uncertainty principle. So you use multi-resolution. You use wavelets of multiple durations, scale factor, and then try to put all the information together and analyze the image with information related to fine detail and coarse detail. Similar to the short-time Fourier transform that is used in speech signal processing, we can apply a window function to the image, fxy, multiplied with a window. The window could be rectangular, square, Gaussian, whatever you want it to be, and then the Fourier transform. This is the short-time Fourier transform. You are computing the Fourier transform not only as a function of frequency uv, but also spatial position x prime, y prime, where that window is located, centered. So that window selects a certain part of the signal or image. The Fourier transform kernel is the same as before. So you compute this for each position of the window as the window is translated, commonly done in speech signal processing as the short-time Fourier transform. Not the Fourier transform of the full signal, but little windows. So in the case of the 1D signal, if you have a 1D signal, take the whole Fourier transform, you get one spectrum. But if you take the short-time Fourier spectrum, short-time Fourier transform, you get as many Fourier spectra as the number of window positions to scan the signal. So it's a 2D function. Now the image is 2D, the displacement is in 2D, so the spectrum is a 4D function. There are some advantages. You are addressing non-stationarity. The signal is changing over time or space, so you are taking small portions and getting the spectrum of what is present there. But then the same window is used at all frequencies, and the resolution is the same at all locations in the resultant space. So that, again, the uncertainty principle says you cannot have arbitrary resolution or arbitrarily fine resolution in both space and time, both time and frequency or space and frequency. If the window function is small, the large scale behavior is lost. If the window is large, rapid discontinuities are washed out. So there is a compromise everywhere. So this is where the notion of scale is introduced. By varying the window function, one will be able to identify both discontinuous and stationary characteristics. So in speech signal analysis, as long as the same speech segment is produced, same phoneme, as it is called, is produced, like ah, you have the same window, keep growing the window, and when it changes, like ask, and is comes, then you say, I'll stop the window, start a new window. And then asterisk T is a plosive, so it'll be a small window when it starts and stops, and so on. So adjust the window size depending on what is present in the image or signal. So you can call that multi-resolution or multi-scale analysis of the signal.